Folks, the stage is yours.
Sure, thank you. So, hello everyone. I welcome you all to this presentation. Good morning, good afternoon, good evening to all of you. And I have my colleague Alex Stryker with me for this presentation. My name is Rajneesh Bharadwaj, and I work for AMD as the Linux kernel engineer for ROCm team. ROCm is Radio Open Compute Module, which is AMD's open source solution for HPC and compute graphics. So my focus area for my work is, kernel fusion driver, which is a subset of AMD GPU graphics driver. But I do have some background on Linux kernel and power management as well. So with that, let's start the presentation. So talking about this presentation, don't bake your graphics card. It sounds unusual, but I'm pretty sure that for this community, especially the graphics people, this must be something either that they have done in the past or must have definitely heard about it. So what is it? Is it fact? Is it mystery? Is it myth? What is it exactly about? So this whole thing of baking the GPUs is not new, and oftentimes people do bake their graphics card in their oven in their kitchen. And why do they do so? Because sometimes when the graphics chips or some of the older electronic components get older, especially talking about GPUs here, and they suddenly stop working, maybe because of the extra amount of stress that they have to deal with, overheating, excessive heating, vibrations due to fan, moisture content. So sometimes the PCB, doesn't work the way it's supposed to. And primarily, the reasons that I mentioned are the reasons. So what people think typically, and based on that belief, they really preheat the oven to 100 degrees, 200 degrees Celsius, put their graphics cards and feel that if there was some broken printed circuit, then the molten solder and the flux, when it again cools down and it evaporates impurities, it will refix the problem. Especially the ball grid arrays, the GPUs that sit on the array. Sometimes it's because of the aging factors. So the loose ends are sometimes fixed and it works, but it's largely a myth, and it works only in 5% of the cases, and most of the times it doesn't. And the reason is that the graphics cards have a typical life cycle of 3 or 4 times of PCB reflow technologies. So if you have an old spare card which is not physically damaged, but was working and suddenly doesn't work, and you believe that it's because of moisture or things like this, you may consider baking it, given that you don't use that oven for cooking, because sometimes these products might contain lead. There can be toxic fumes, gases, which can contaminate, and of course, the heat distribution in the normal oven is not uniform. We need special ovens for PCB reflow technologies where the heat distribution is usually non-uniform. Some of the larger components, such as GPU, they tend to sink more heat, so they tend to be heated more, and the smaller components, if heated to the same degree, might actually get burnt. So it's a dangerous operation to do in your own oven, but if you want to do that, remember this disclaimer, it's an expert thing, and you must be very lucky, and don't otherwise try this thing at home. But this talk is actually not about baking, especially the graphics card. It's about similar sounding technologies called BOCO and BACO. And interestingly, these technologies help in keeping the graphics card cool, save power, so that you don't have to bake your graphics card, because it might end up longer, because now it's only used, the graphics card turns up only when it is really used. Otherwise, it remains in a silent mode and less power saving state. So this is basically the theme of this presentation. So with that, let's move ahead. But before we get into the details of BACO and BOCO, let's get rid of some buzz and chip jargon. So B stands for buzz, O for off, C for chip, and A for alive. So BOCO means bus off, chip off, and BACO means bus alive, chip off. And we are talking about the PCI bus here. So that's about this. And then further, let's delve into the specifics of BACO and BOCO. So BACO and BOCO, before we go into these technologies, I want to give a brief background about BOCO and BACO. So BOCO has been around for a while, and it was originally introduced with AMD's Power Express technology. And later it evolved. We had something like BACO, but the support for BACO in Linux was recently completed, although it has been existing in some patches for some other activities like GPU reset for a while. But for the runtime power management, it is recently made available as part of mainline Linux kernel. I want to talk briefly about the device power states because it essentially is about device GPU power states. So D0 is the device state where the device is fully operational and functional, and D1, D2, and D3 are the device low power states. These states have varying degree of power consumption, context saving with driver and firmware, varying degree of resume latencies, and different wake up capabilities. PCI spec further defines two more substates of D3 state, which is the lowest possible power state of a device, called D3 hot and D3 cold. So think of D3 hot as a state where the power is not physically removed from the device, although it is turned off to a larger degree. On the other hand, D3 cold is actually like removing the power from the device, and it is essentially turned off. But in some cases, the device might still draw a very low amount of current for sideband access, but most of the times D3 cold means it is completely cold and turned off. There is no live wire connected to the device, basically. So BOCO basically powers down the GPU completely and offers more power savings. So BOCO is sort of, you can think of BOCO as D3 cold. And BACO, which has the main contrasting difference with BOCO, is that the PCI bus is kept alive. The PCI configuration space is always available for the operating system to look at. So that's BACO for you. We'll look at the characteristics of BACO and BOCO in coming slides. Yeah. So as I mentioned, BOCO was introduced earlier, originally with AMD Power Express laptops, whereas BACO was, a low power solution for DGPU, especially targeted at hybrid and desktop segment. BOCO is mostly handled by ACP. It used to be handled by ACPI ATPX methods, and now the PR3 runtime power management methods. And ATPX methods and these methods are actually defined in the ACPI tables for the device as part of the system BIOS. BACO, on the other hand, is largely initiated by the device driver, and once the entry to the D3 hot state is triggered by the PCI device driver, then internal underlying SMU firmware takes care of handling all the low-level interactions, shutting down the clocks like SPLL, DPLL, etc. The bus interface obviously remains on in case of BACO, so the device is always discoverable. But in case of BOCO, it completely disappears from the device. Talking about the wake up latency and power savings. So obviously BOCO saves more power for us, but at the cost of more resume latency. BACO, on the other hand, gives good amount of power savings, including the fan control. The fan completely turns off when the device is not in use, and it offers the better wake up latencies for the resume operation compared to BOCO, because in this case of BACO, the bus interface is on, so the retraining of the PCI link is not needed. The only thing that is still required in case of BACO is the VRAM or the memory modules retraining, which is much more in case of BOCO, because BOCO has to deal with memory retraining as well as the PCI link reestablishment. Yeah, so this is about BACO and BOCO, and how do they converge into the larger picture is what we're going to talk about now. So I mentioned that BACO was originally meant to save power, but it was initially being used to have the GPU reset mechanisms in place, and later the support was extended when the things became more stabilized for runtime power management on Linux. But before we go into the specifics of runtime power management, I want to briefly also talk about the larger scheme of runtime, the Linux power management scheme. So broadly, we can classify the power management on Linux in two different or in two ways: the system-wide power management and component-wide power management. So system-wide power management is the framework where you really have a user input, or a user space has some say in initiating the suspend trigger at the system level, not just the device, but the whole system suspends. So there are two things here: suspend to RAM, also known as legacy ACPIS3, and the recent contemporary suspend to idle, which is an advanced power saving technique in Linux kernel. Especially the advanced states like S0ix states are achieved through suspend to idle. On the other hand, talking about dynamic power management, there are various frameworks available for us in the Linux kernel, such as CPU frag, device frag, runtime power management, OPP, operating point performance, GenPD, clock framework, regulator framework, and so on. But for our case, we are interested in runtime power management because we are actually talking about the graphics power management here. So, so the most important, data structure here for power management in general is dev PMOps, and it provides some callback hooks which device driver is supposed to implement, and the runtime underscore suspend is basically the hook that is called from runtime underscore idle method, and this is completely device initiated and is autonomous. So there is no user input here. When there is an activity on the device, it is the responsibility of the device driver to detect it and make sure that the runtime idle is called, and then eventually runtime suspend is called. And with that runtime suspend callbacks, the AMD GPU device suspend methods are triggered, which eventually lead to BACO or BOCO, depending on the ASIC and depending on the underlying hardware that supports it. So there are some helper functions here as well, especially to support and enable the proper working of the graphics driver. We should look at some important functions here for PM runtime. There are two variants here largely, get variants and put variants. So get variants are basically the variants which make sure that the devices do not runtime suspend until the reference count held by calling of these APIs is in place. And once the actual workload is done, let's say you're running a compute kernel or a graphics or an initiator, and if that thing completes, now you have nothing else to do. So in that case, it is the responsibility that a corresponding PM runtime put sync or put auto suspend is also supposedly called by the device driver. So the way these APIs work is basically on a simple concept of a reference counter. So when we want to do some meaningful work, we need to hold this sort of a reference count, achieve the work, and when the work is done, we have to release this. So there are various APIs, and this is what is used in making the BACO implementation for a runtime suspend framework. To support BACO, we had to deal with some other dependencies. Obviously, we are talking about device D3 states here. So graphics alone cannot be put into D3 if we have dependencies on display audio, especially the HDMI audio and all the codecs related to it. So they need to be runtime suspended also, without which the GPU cannot be put properly into runtime suspend methods. So there were some broken pieces here, especially with regards to the legacy, VGA switcheroo related problems. VGA switcheroo is basically Linux subsystem for hybrid laptops graphics, and it used to come in two different flavors, Muxt and Muxless. Basically, these are both are dual GPU systems with a multiplexer chip to switch the output between multiple GPUs. So you have integrated GPU as well as a discrete GPU, and with the Mux method, you can have them both. But on a muxless setup, there are two GPUs, but only one of them is actually connected to the output at the time. So there were some refactoring required because of some legacy ATPX and power handling issues with that code, which was recently fixed in Linux kernel 5.6. So with that, the only pending piece to support BACO completely on Linux for runtime power management was the kernel fusion driver. So KFD, as I mentioned briefly earlier, is a part of AMD GPU driver. It used to exist as a separate entity earlier, but now it is a part of proper AMD GPU Linux driver. And it works together, but it doesn't have its own power management implementation. It relies largely on the initiated callbacks from AMD GPU. KFD driver is used for compute. Somebody had something to say? Okay. So the KFD driver is used for compute applications, supports runtime, supports user mode queues. And the way we worked around this was basically we looked at the bare minimal entity that we could consider as a valid workload. And what we found is that we use the per process device data, PDD, as part of any active queue. And for the whole life cycle of this PDD, until this PDD is destroyed, we hold the runtime PM lock, and we release it only when the PDD is completely destroyed. So this change also landed in the Linux kernel, I think, earlier this year. And with that, it basically laid the foundation of completing all the missing pieces to enable BACO completely. So right now, if you boot the kernel with run PM enabled, which is the default setting also as a module param, you will see this BACO already kicking in. So I think you should be aware of the fact that if you see the GPU going idle after 5 seconds or so, it is because of the fact that BACO has kicked in, and we have programmed 5 seconds as the default auto suspend timeout for BACO trigger for runtime suspend. I want to also briefly mention about the GPU reset techniques here, because BACO is also used for resetting the GPU. The module param AMD GPU reset method can take various inputs. Basically, it tells us which mode we would like the GPU to be reset with. Mode 0 is a legacy mode, is not used, but what largely is used on the contemporary chips like Navi and Vega is mode 1. It has its own limitations. Then we have something called mode 2, which is mostly used for the APUs, because mode 2 is lesser reset than compared to mode 1. And in mode 1, we reset most of the IPs. In mode 2, we don't reset, it's a limited reset. Like we basically don't reset graphics and multimedia. So especially, the access to VRAM, the system memory on APUs is a contention. So we cannot use mode 1 on those things, on those chips. So we use mode 2 for that. And BACO is ultimately used where everything else apparently fails, especially in case of ECC and RAS errors. Because when we use mode 1 for resetting, it takes ultimately the path is through PSP to SMU, but it also relies on access to the MM hub. And if there is a problem with MM hub access itself, then maybe because of the sync flood or whatever reason, the response to the driver might be forever delayed, and it might not really serve the purpose. So for that purpose, we can use BACO to trigger a reset, especially for RAS and ECC scenarios. There is a debug FS interface also available called AMD GPU recover. If you read this file, if you do a cat on this file, it can also manually trigger a GPU reset, and it internally checks whether the underlying chip is supporting BACO. And on the next fence and wait, it basically implements the same GPU reset mechanism. So current cut stream status, it's fully available upstream. Don't boot your kernel with run PM disabled. And if your graphics card, if your AMD graphics card is supporting BACO, it will be automatically enabled. So if there is no active workload, the graphics device should ideally suspend within 5 seconds. You should see fan spinning down and eventually coming to a complete halt. And if you are using the graphics card for compute, the same behavior will be observed. So I've also listed down the important APIs that one might look at if somebody wants to understand internals of BACO, the SMU interactions, how is it basically set up by the device driver, and how the entry and exit sequencing is performed. The main algorithm for BACO entry and exit is implemented inside the firmware, but the responsibility of the driver is basically what these APIs cater to. So with that, I think I have come to an end, and I would like to end this presentation now with a note of thanks to my colleague Alex Stryker and Felix Gueling for their support. So thank you. Open for questions now.
Okay, thank you very much for your presentation. Seems like the chat is very hungry because they are talking all about bacon and baking. There's also one question. So what is the absolute amount of power used by the entire device in BACO state? Also, how does it compare to the state before the BACO was implemented?
So it's very subjective to talk about the absolute power, but think of it, if suppose there is no runtime PM implemented, and the GPU is always kept alive, especially for compute. So for compute, we never had this working, even if the kernel supported it. But for compute, we used to boot the kernel with run PM disabled, and our GPUs were, always burning the power to the full throttle. And whatever power management was implemented in the firmware. There was no real power management happening from the kernel or driver side. So with that, I think right now the scenario is if you have a compute kernel to run, then only the GPU will be woken up. If the device is already suspended, it will be woken up. The lock will be held. When the workload is done, the lock will be released and the GPU will suspend again. So compare it with, fully working state of a GPU, which is, we are talking about watts here, not milliwatts. Versus when it's suspended, we are talking about few milliwatts.
Yeah, so I mean, like in the case of like BACO, for example, if you have an idle GPU that's still powered up, depending on the GPU, you're looking at anywhere from like 5 to 7 watts generally, on a desktop card, and then substantially less than that, like a few milliwatts once it's in BACO state, and no power at all in the BOCO state.
Okay.
I don't know the exact measurements offhand, but something like that.
Okay, thank you very much. That's it for the questions, and you were the last presentation of the day, so we're closing for today. Thank you.
All right, thanks.